We have a German living in Switzerland sitting on the first row, so let's start on time.
I'm silent.
Hello everyone, and welcome. My name is Anders, and some of you might know my C++ quiz site, cppquiz.org, or my blog, C++ on a Friday. I'm also on Twitter as Knatten. And today I'm going to talk about null, and specifically how and why to get rid of null. And the reason I want to do that is I recently worked in a largish C# code base where we just by convention had banned null entirely from the code base. And that was really nice, a really pleasant experience. And then I had one data point of something being subjectively good, and then this is software development, so then it's time to start evangelizing and making talks and convincing everyone to do the same. In C# there are no general good solution for non-nullable types. And in C++, we of course have those, so that gives us certain advantages if we are trying to do the same in C++. I noticed a few C++ experts arriving, so there's nothing very fancy or anything going on in this talk. So if you want to have a nap or something, I'll wake you up after the talk. The outline of the talk is going to be first, why are we using null today? Then why null is bad? And what can be done about it? So pretty classic setup, I would say. Before we start, let's hear what the inventor of null has to say about null. Unfortunately, they didn't give me any audio out, so the text is up there, and if you listen carefully, you might be able to hear what he's saying.
And that led me to suggest that the null pointer was a possible value of every reference variable and a possible mistake on every use of that reference variable. And perhaps it was $1 billion mistake.
Right, so that's Tony Hoare. He invented null.
He's Brit.
Yeah.
He's a Brit, so
Yes.
billion is actually a billion.
Yeah. Yeah, so Tony Hoare isn't just some random dude. He invented quicksort, he invented Hoare logic, he got both the Turing Award and the von Neumann medal, and he was knighted. So he's a pretty clever guy, but he did invent null back in the 60s while working on Algol W, Algol in some sort being a predecessor to C++ in some way. He had a very good reason for doing so, which we will get back to. And the $1 billion is, of course, his personal guesstimate. He seems fairly certain it's on that order of magnitude. But I think we can all agree that from the 60s up until now, null bugs have probably cost society quite a lot of money with all the crashes and everything. So given that both Tony Hoare and myself are quite hostile towards null, I thought we should start with some reasons why null is good. So do you have any favorite things about null? What's good about null? OK?
Simple way of terminating anything.
Yeah. Yeah, including the program.
List.
Yeah.
How should you decide where it stops?
Yeah. I'll cover some of my reasons why null might be good. So we have a function which might not succeed. It's called getThing. It will try to get you a thing. It doesn't always find a thing for you. So as a part of normal operation of the program, sometimes you find a thing, sometimes you don't. It's not an exceptional case, so you don't use exceptions. So the typical old school way of doing this is you return a pointer, because then you can just return a null pointer if you couldn't find anything. And I will be using raw pointers all over this talk. All the points apply for smart pointers as well, but with raw pointers, everything fits on a slide, and I don't get into discussions about how you should use this smart pointer instead of that one. So this is the normal good old way of doing it. You call getThing, and then you check, did you get something, or did you get a null pointer? So only proceed if you actually got something. The other way around, it's a way to also provide an optional parameter. So say you have a doWork function. It takes a work item to work on, and then you can pass it a logger if you want logging. So the way you indicate it here is you pass a null pointer if you don't want logging. And if you want logging, you do as you do on the second line here. You call it with an instance of the logger interface or the abstract base class. So it's one way of doing optional parameters. It can also be useful for late initialization of members or variables in general. If you can't initialize the variable when you declare it and you want to still initialize it, but you don't have a value yet, the only default value for a pointer is, of course, then null. So in our little business logic here, we're modeling nuclear physics. We have an atom which points to its nucleus, and you have the nucleus which points to the atom. And to be able to initialize the atom, you need to have a nucleus to point to. And to be able to initialize the nucleus, you need to point to the atom, right? So how do you initialize both of these structs in the constructor? You can't really, not fully. So what you do, of course, is you initialize the atom with a null pointer for the nucleus. Then you create a nucleus pointing to the atom, and then you revisit the atom and set the nucleus pointer. So you get that two-stage initialization. But you need a null pointer until you have everything ready. And this type of cyclic references is what motivated Tony Hoare to invent null when he did. So null can be good for functions which might not succeed, as we saw with the getThing function. Sometimes it doesn't get you a thing. Optional parameter where you can just pass a null pointer if you don't have a value, or for late initialization of variables. So null is good for indicating a missing value. So we've seen some good use cases for null that are typically found. So why is null bad? Why don't I like null? Yeah, dereferencing a null pointer is undefined behavior. So if you have a getThing function returns a thing we saw earlier, if it's null, and you try to call something on it, or you try to take a value, or you dereference it in some other way, that's undefined behavior. And someone said segfault. That's what you typically get on the systems I usually work on. I talked to Alfred this morning, and he reminded me that some of you probably don't even get the segfault. Some of you can actually just use the null pointer, and that's just some part of memory that you can actually use.
At least address null.
Yeah.
Not necessarily. If you say null pointer, the compiler is usually trying to
Yeah.
prevent you, but yeah, the address.
But if you use the address null, some of you are probably, many of you are embedded developers. Maybe you don't have an OS that will actually give you a segfault. So even though it wasn't undefined behavior, maybe you got a null pointer exception or something, it will still be a bug because this doesn't make any sense, right? So you then end up checking for null. This is exactly like we saw on the first slide. We try to get a thing. Did we get anything, or is it a null pointer? If we got something, we will do something. And this is fine. This is the intention of how this function is designed. You are supposed to check because it doesn't always give you a value. But when you start checking pointers, then since any pointer can be null, then every pointer can be null. So how do you know which ones to check? So you get the thing, check if you got the thing, you do something with the thing. The thing has a device that you also want to do something with. But this is a pointer, so you need to check that as well. And suddenly you can end up checking for null all over the code base. This will make the code less readable and slower. The presence of null will lead to unclear APIs. We saw the getThing function. It might return you a thing, or it might return you a null pointer. And that's fine. That's part of its interface. But you can't see that from looking at the code. The same with the doWork function. Are you allowed not to give it a logger, or does it require a logger? You can't see it from the interface of the function. The thing, does it always have a device, or does it sometimes not have a device? You can't see it from the code, so we have to go check the documentation and hope that it's well documented. And when you upgrade to the next version, let's hope they didn't change any of that. So if the getThing function always used to return you something, and now they've changed the API so it doesn't always do that, or the logger didn't used to be mandatory, but in this version it is mandatory, your code won't break because the interface changed, but the code doesn't reflect that it actually has changed. So you better pay attention to the changelog, or maybe even read some diffs if they forgot to mention that. So yeah, unclear APIs. I'll introduce some classification of like how I personally classify bugs from bad to good, or at least from aren't really any good bugs, but from worse to better bugs. which will be useful. The first classification is where is the bug discovered? Is it discovered in production? You have released your software, the user is using your software, and you get a null pointer dereference and the rocket crashes or whatever. Hopefully, maybe it gets caught by some manual process, like a code review, or your manual tester is able to crash your program. Would be better if you had automatic tests like unit tests, system tests. Would be really cool if the compiler could catch your bugs. So for null bugs, at least for me, it's typically like something got into a weird state that I never thought about. So maybe it's not found until here on the top here. I could write automatic tests for every pointer in my system saying, hey, what happens if this is null? But that's going to be really expensive. The other scale is when is the bug discovered as compared to when it actually happened. So is the bug discovered when the effect of the bug is visible at effect time, or is it found at cause time when the bug is actually caused? So it's easier with an example. For nulls, well, for most of us, you discovered it at effect time. You discover it when you dereference the null pointer. But the bug happened previously when someone wrote that null pointer. That's probably the actual bug. But you don't discover that you have a bug until you try to dereference it at effect time. And yeah, if you can just do whatever with a null pointer in your program, it's none of this. It's like up here somewhere. It's really bad because you will just other things might happen. And when you discover bugs at effect time rather than at cause time, then your stack trace is useless, because the stack trace will only tell you, OK, what were you trying to do now? It won't tell you what did you do when the bug happened. And the same goes for your error reports from your users, because they will tell you, I clicked here and the program crashed. But that's not where the bug was. The bug was when they did something else previously. Or maybe it wasn't even them doing it. So they will also be quite useless. So in summary, that slide will be back. Why is null bad? Dereferencing is undefined behavior, and even if it wasn't, it would still be bad. You might end up checking for null everywhere, and APIs get unclear because you don't really know. Here's one of the many examples we saw. And yeah, finally, null bugs, many of them at least, can be caught very late in the release process, and at effect time when the bug is visible and not at cause time when it's caused. So little interlude. Why is static typing good? I will assume that many of you write C++ from time to time, or C or some other statically typed language. So what are your favorite properties of static typing? Why do you like it?
Compiler errors.
Compiler errors, yeah.
It's fast.
Yeah. So an example again. A function f taking a person, and I'm trying to pass a company. So this doesn't compile. At least in Norway, it doesn't compile. In the US, I think this compiles. But the point is, I get the compiler to tell me. There's no possible way for me to actually pass in something wrong unless I intentionally do bad things. And that means I don't need to write any tests for what happens if I pass something else on a person. And inside of f, I don't need to check whether I got a person or not. And also, I can just look at this signature of this function, and I can know quite a lot about what the function expects and what it promises. Of course, this is a simple one, but a signature will tell you more when you have static types. So static typing is good because a whole class of errors are caught at compile time instead of at runtime. Less tests to write, less code to write, and it makes the code easier to understand. So what does null do to static typing? So normally you would say this function requires you to pass it a person. You have to pass it a person. But when you have a pointer, that can be null. So what it's saying is, you have to give me a person. Or not if you don't want to. You can just pass me null. And the same goes for a return type. Like, I promise to return you a person. Or maybe I'll just return null. So every time you use a pointer, you say you don't really require that type anymore. It could also be null. And I would say in some sense it circumvents the type system. Or the fact that something can be null, nullability of something, kind of circumvents the type system. So we had our list of why null is bad, and yeah, from the discussion of static typing, I think we can add also that it sort of circumvents the type system. So we've seen that null is useful for many things. It's also harmful in many ways. So the question then is, how do we go about creating this beautiful new world with no nulls without losing the usefulness that we have seen? Yeah, we talked about null and nullability and possibly missing values. We have been a bit unclear about terminology, so let's think about requirements and implementation details. So there's a requirement to be able to represent values which can be missing. And the implementation detail is then the techniques which support missing values. Yeah, so this is our requirement, possibly missing values. This is our implementation details. How do we represent those values? So some values which can be missing. A person might or might not have a phone number. A print function might take a color. If you don't give it a color, it will just use the previous one. Function might or not be able to find the thing you asked for. So let's call these maybe values, values that might or might not be there. And that's the requirement we have. We need to be able to represent maybe values. And then we have techniques which allow for missing values. So we saw pointers. That's the old way of doing that. In C++17, we get a real maybe type, a proper maybe type called to the optional. And there are other techniques to use, like the null object patterns or other techniques. But I won't focus on that today. So let's refer collectively to these as maybe techniques, and then the maybe type being one of these maybe techniques. And the most basic thing that I think everyone is already doing today, or at least quite a lot, is to realize that maybe techniques are for maybe values. If you have a definite value, you know it's going to be there. Don't use a type which allows it not to be. And this is nothing new or fancy. It's old school stuff, but I think it has to be mentioned as the first step. So I'll use some examples now from like some example code for the music industry, since I love music. And we have a class designer. The designer can make a flyer for an artist. Okay, so we have to pass an artist, because if you don't give an artist, there's no way to make a flyer, because there's nothing to make the flyer for. It's not optional. So how do you fix that function?
Artist reference.
Artist reference. Okay, this is very, very simple stuff. I think we were all doing. It's very clear now that you have to pass an artist. You know when you read the signature that it's not optional. And it also clarifies ownership. There's no way that Makeflyer is going to take ownership of this artist. I mean, it's pretty clear from the name of the function as well, or from the context, that it wouldn't be true. But in many other cases, it's not always that simple to see at once. How about this example? You have an album, and in our business logic, every album has to be made by one artist. So we have a pointer to the artist that made the album. Would you change anything about this? Would you make it a reference? I would probably make it a reference. Because of the same arguments as before, it communicates very clearly to anyone constructing an album that you have to give an artist. It's not optional. And you don't risk null pointers. You don't risk anyone passing null. And in client code, if I have an instance of album, I don't need to check whether there's an artist. I can just know that there's always going to be an artist available for this album. And again, ownership is clear. I'm just referring to this artist that you're passing me in the constructor. You are responsible for the lifetime and for deleting that object. But this has some consequences. I'm initializing the artist member in the initializer list. And that's not only because it's good practice often to do that, but you have to. But because when you have a reference, you can't make it refer to something else later. So that's the only place where you can initialize a reference. You can't initialize it in the constructor body, and you can't initialize it after the constructor. So that might be inconvenient in some cases. But what it does is it pushes you toward immutability and fully initialized objects. So you have to initialize everything at once. And it pushes you away from two-stage initialization and stuff like that. What if I want to add an assignment operator to this class? OK, I can't do that because I can't make the reference refer to something else. So I can't really write an assignment operator. But in most cases, I would say you don't want to have an assignment operator. And if you don't have an assignment operator, you're not going to reuse your variable. It pushes you towards immutability again, which is good. And so if you can do without that, then this is great. And it will often push you towards a safer style of coding, I would say. If you really, really need to be able to do any of this, then you can use a reference wrapper to put around it. But I hope at least mostly you won't need that. References isn't the only thing that can replace pointers. Often you can replace a pointer with just a normal good old value. So say we have to put a date on the flyer because you have to put which date the artist is going to play. The date class is probably just ticks since some time or something. If it's a small and trivial class, this is going to be just as cheap as a pointer or a reference. So that was members and arguments to functions. What about return values? We saw the make_flyer function. It returns by value. So maybe the flyer is a quite big class with lots of graphics and fancy things. So when I call make_flyer, then you would have to initialize the flyer in here, and then you have to copy it out into this one, right? But since we have the return value optimization in C++, it says that you're actually allowed to skip that copy. Even if the flyer has a copy constructor with side effects, all of that can be skipped. That's a very rare type of optimization where the optimizer is allowed to actually change the observable behavior of the program. You don't have to run the copy constructor. But it's very handy, and you can usually rely on this happening. I wrote a
In C++ 17, it's guaranteed with direct initialization to
do
that without even making the type copyable.
Yes, but isn't that only if you're returning a PR value or an R value?
It depends on what you're doing
Yeah. Yeah. At least it's true in some cases in C++, you're actually required to skip that copy. So what you just do is you just take this memory that you're going to copy into later and just use that memory inside here and just fill that up at once, and then you can skip the entire thing. I wrote a blog post back in 2011 where I tried several compilers, giving them some tricky cases with like chained calls and stuff. And all the big ones were pretty good at it. And people have been submitting their results since then. And Clang, GCC, and Microsoft are all very good at the return value optimization in my experience. But tests on your system if you really care about it. It's very easy to check. You just might make a type that just does cout in the copy constructor, and then you check did you get a cout or not. So there's one case where you can't return by value. That's if you have a polymorphic type. So say the flyer is a base class, and you don't know which base class will be actually returned. You can't. If you return by value, you only get the flyer type. You slice away the child part, which is bad. So you have to use a reference or a pointer. But you can't return a reference to a locally created variable because that goes out of scope when the function exits. So in those cases, you will often end up with a pointer, and probably a unique pointer. One final simple thing, use the standard library. We want to show the lyrics for a song. So we pass it a const_char pointer to the lyrics. Or since we're C++ programmers, we pass a reference to a string instead. That has many advantages. the important thing for this talk is that lyrics is never going to be null. It can just fine be an empty string, but it's not going to be null. And let's say we want to invite some artists to our festival. So we point to the artist array and give it a number of artists to invite. Or we use some sort of container. Or maybe we pass it some iterators or span or a range or whatever. But at least we don't pass it a pointer. That's the important part. So maybe techniques are for maybe values. Use references or values instead of pointers. Return by value. Know about the return value optimization. And use the standard library over old C-style signatures because they really like pointers. So here's the classification again. What has all of that given us on these scales? All our old pointers that now are references or values, that was possible bugs around here. It's just, wouldn't even call it a compiler error. There's no way of compiling a program with null there. So it's not possible to represent in C++ the bug you were actually trying to write. Yeah. So that's how to deal with definite values. You know we have a definite value. Use a definite type. Don't use a maybe type or a maybe technique for a definite value. But not all values are definite. Some values are maybe values. They might not be there. And then let's see how to turn a definite value into a maybe value. In C++ 17, we got the optional, a real maybe type. It's sort of like a tuple of a bool and a possible value. So either it has true and then the value you're looking for, or it has false or no value. So it's a very, very simple type in that sense. A few examples. Say you have an optional artist. Then either there's an artist there or there is no artist there. So you can say if A has value, do you have an artist? Or you can just use the bool operator and just say if A. And this looks exactly like it did for pointers. When you're testing for a null pointer, now you're checking if it has a value. The big difference is that now it's an optional type. It says right there, optional. You know it's going to be optional. That's why you have to check. It could be a pointer for a whole host of other reasons than for it to be able to be optional. So this is a lot clearer. Then you can get at the value by calling .value, and it will throw you an exception if there was no value. You can also just dereference it if you're brave, but now you're back into undefined behavior if there was no value. And it has a handy arrow operator, just like pointers. So both of these also look exactly like for pointers. It's undefined behavior if there's no value, but it's still very useful because then you can check at the top of your function, and then you can just dereference it for the rest of the function when you know there's a value. So we can get fast executions. We don't have to pay for the check every time you access it, right? So let's say we have an artist, and we ask the artist to go write a song. So they will go and try to come up with something, but it's really hard to write a good song. So maybe they don't always come back with a good song. So instead of returning a pointer, like we saw earlier, we can return an optional song instead. And why is this better than pointers? Well, it's someone bothered to actually write std optional in here. So you know it's optional. It's very clear from the code. It might also be good for performance because the value of an optional is the memory is inside of the optional memory. So all the memory is allocated in one place. It's not like it has the bool for saying, do you have a value? And then it's pointing to the value. No, the entire value is inside of the optional. So that means you get very good locality, which is good for cache. And you get fewer allocations. You don't get an extra allocation like you get, for instance, for a string where the actual string is somewhere else on the heap. And the return value optimization still applies, so you don't actually have to copy this out at all. Back to the make flyer function. Let's say you don't always have to put a date on the flyer. Sometimes you just want to make a flyer for the artist just for advertisement. You want to make date optional. Just wrap it instead of optional. Now you get an extra bool and maybe you get some padding for alignment, but it's still a small and cheap trivial class to copy, which should still be quite performant. So optional is great for small value types. What if you want references for some reason? Say you have a superstar class, and our superstars, they're really big superstars, very expensive to copy. Or maybe you just want reference semantics for some other reason. What do you do then? Well, the obvious thing, of course, you just pass an optional reference. But optional references are not supported by optional. You can only have optional pointers or values. And there's nothing technical preventing us from implementing this. It's just that people haven't been able to agree on what does an optional reference mean. The semantics are unclear. I talked to the poor guy trying to to gather consensus for what it should be, and I don't think we'll get this for C++20. He seemed sort of like sad about the whole situation. Yeah, so you can't have an optional reference. What do you do instead? Maybe you just give it a reference to the optional. In some cases, this is actually great. If you can always know that the caller of this function has the superstar already inside of an optional, then this is great because you can just refer to that optional with the superstar inside it. If I want to call this function and I just have a superstar object, and I need now to pass an optional superstar, I have to first create an optional superstar. So I have to copy or move the superstar into an optional, which is going to be very expensive, especially if I can't move it. So this only applies if you really know that the superstars, they are always inside of optionals anyway, so it's not a very general good solution. You can wrap a reference wrapper around the reference. Then the signature doesn't look as nice anymore, but at least it works. You could just give up on this stupid no more nulls idea and just send a pointer instead, because pointers you can put in optionals. But that doesn't really make sense to pass an optional pointer, because even if you have a pointer, that pointer could be null. So then you have to check, did I get a value, and was that value not null, and then I can do something. So maybe you just give up and go back to the good old pointer. Depends a bit on the use case, but I think the optional reference wrapper is a pretty good option here. Yeah?
I think the next to lowest line, optional with a pointer, it states very clearly that the f function can take that you don't have a superstar.
Yeah.
So that makes it much more clear than the const superstar pointer.
Yes.
Version.
Yeah, it makes it much more clear. And I'll skip ahead a little bit and say that this is kind of, you can't really compare to C#. This is what we did in C#. And we didn't, and that did help a lot because of that reason, because it communicates very clear. So I agree with that.
One tiny question: are you sure all your consts are in the right place?
No, I'm not. I'm on the fence about that. So what does std optional give us on this classification? I would say it doesn't give us anything. But what it does, it makes the API a lot clearer. So we're a lot less likely to make the error in the first place. And the error here being, of course, using the optional value without it actually having a value.
Actually, I think it does do something to the second point on where, that is, it increases the chances of discovering errors in code review.
Yeah, that's a good point. It increases the chance of this happening. But just the fact that it makes the API a lot clearer, it makes you less likely to make the bug in the first place, and more likely to that it will be discovered if you forget. So we cleaned up a lot. We got rid of a bunch of potential nulls by using references and values. For definite values, for maybe values, we used std optional, and we've come quite a long way. But there might be some remaining pointers in our code base. Okay, maybe you need to point to some physical address. You need to return a polymorphic type from somewhere. You need to allocate some stuff on the heap, or you have many reasons for maybe having some remaining pointers that you couldn't replace with the previous things we saw. And some of those pointers will be allowed to be null at times, and some are never supposed to be null. So either we can do something with the maybe pointers, the pointers that might sometimes be null, or we can do something with the definite pointers that are never supposed to be null. And yeah, this is where I was going to say basically what you comment to that. We only did something with the maybe pointers in C#. So we got no help from the compiler or the runtime or anything with our definite pointers actually checking that they're not null. But even doing just that made the code a lot easier to understand. And every time we saw a null in the debugger, it's like, hey, something isn't set up properly here. You didn't need to really know that part of the code to know that something was wrong. So which one should we do for C++? So we have two thing pointers, a maybe and a definite thing. So the maybe thing might not always be there. The definite thing will always be there. And we want to call do something on both of them. So what about wrapping the optional, the pointer in an optional? That's what we went briefly into earlier. Well, first of all, now you have to dereference it twice. So first you have to dereference it to get it out of the optional, and then you have to dereference it to do something with it. So it gets a bit ugly. But the worst thing is that when you check if it has a value, that value might still be null. So you will have to even check this in addition to this. So maybe pointers, they don't make that much sense always. Instead, we could tackle the definite pointer. We could wrap it with not null, which you had some issues with yesterday, or was it this morning?
I'm saying a reference might work as well.
Yeah.
You can't reset that, but that might be a good idea.
Yeah. So use a reference if you can. But if you, for some reason, have a pointer you have to use, you could wrap it in not null from the guideline support library. I'll get back to the details, but it's a class template which ensures that this pointer will never be null. So now for the maybe pointer, we're back to the good old check if it's there. If it's there, you do something. But this is what you want because it's a maybe value. So you're supposed to check for it. For the definite pointer, you can just call do something because you know it can't be null in the first place. So this wins us quite a lot, actually, because then you only need to have these null checks for the pointers which are actually allowed to be null, and you don't need to have those checks in the other places. And it makes the API clearer. If you see just a raw pointer, you know it's a maybe pointer. If you see a not null pointer, you know it's definitely going to be there. GSL not null, it's just a normal class or class template. The constructor taking a null pointer has been deleted. So initializing this with null is now a compile error, which is very, very nice. So what would previously be a runtime error is suddenly a compile error. This doesn't only go for the null pointer type. You can also pass a 0, and you will actually compiler will tell you that, hey, this isn't allowed. But it's quite easy to just pick another constructor, right? So if you have an existing raw null pointer, you can pass it in, and now the constructor won't, or the compiler won't help you. But now you get an error when you're trying to assign null to this pointer. You're trying to set it to null, and you get the error when you try to set it to null, rather than when you try to dereference it later. So you get the error when the bug actually happened. And if you have a good static analyzer that knows about not null, at least this trivial case would probably be picked up by the static analyzer. So yeah, I said in the beginning I'm using raw pointers. Everything applies to smart pointers as well. Not necessarily with not null. You can't use not null with unique pointers, at least not right now. So it's not always a solution you can use. So what does this do for us? Some of the cases that used to be up here, if you try to initialize it to null in the source code directly, it's a compile error. So we took all of these down here. And for the rest, we took them from here down to here, because we now notice when we try to set it to null, rather than when we try to dereference it. Or if you're working on some system which doesn't give you a seg fault or a page fault or whatever, which maybe is up here, then at least it brings you down here. So GSL not null helps you because you only need to do null checks on your maybe values. Less code to write. The API is clearer. And your definite pointers will be either checked at compile time by your static analyzer or at runtime, without you having to do anything else than just mark it as not null in the declaration. So what can we do? What's the bright future? What does it look like? We use references or values over pointers. We use std optional for optional values, and GSL not null for definite pointers. Then we get clearer APIs, less code, fewer tests we need to write, and actually many of our previous bugs, they won't even compile anymore. No more nulls. Did we get there? We didn't really get all the way, I think. Like, it's not like in Rust where they just say there is no null, right? That they don't have null. We still might have some nulls around. But we got rid of a whole bunch of them, and we have some safeguards that we can use for the remaining ones. Right. Give me questions. Alfred?
Linked list. Linked list.
A linked list?
Don't. It's the worst data structure ever.
If you need a linked list?
Okay, a tree, whatever, any data structure. I think you'll see pointers in the standard library.
Yeah.
How those data structures are implemented.
Yeah. Then it's at least it's contained in a library.
Right.
So the standard library is fairly well tested and used by a lot of people. So it's at least safer than if you start doing it yourself. And if you need to make any data structures like that yourself, I guess, then you will hopefully treat it as library code and test it extra well.
Is it possible to make a recursive data structure which has elements of itself? An optional with a optional structure that includes an optional structure of itself?
Yeah.
Sure. No.
Yeah. No?
Not with a
Because
optional.
when you have a member as the optional of the same type, the type is still incomplete. You cannot actually.
Oh, right, of the same type. Right, OK, now I understand what you mean.
can have reference or pointers
Yeah.
while you're defining a structure.
Yeah, I misunderstood your question.
So with optional, you can't give it memory that's already
No,
allocated.
you can't. And that might be a concern. If you want to transfer a raw object of something into an optional data object, you have to copy or move it into the optional. So that might be a concern.
Because we typically have packets coming in, we have
Yeah.
memory already. For example, we have pointers already in memory when we boot, right? Tables with pointers, I guess.
Yeah.
We try to not make them into pointers
Yeah.
as an internal, as a code representation. But
Mm.
I don't know.
Yeah. No, that's it's a kind of a performance trade-off. Do you want to have good locality, or do you want to be able to point to already existing stuff? If it's for internal use, I guess it's making an optional type is very, very simple, especially if you don't need to allocate the memory for it yourself. Then it's just a bool and a pointer. So maybe you could make your own. I don't know.
You did mention the combination of optional and not null. Is that a valid way of?
And optional, yeah, actually, I had it on my slides for a time, kind of for fun. I had an optional of not null shared pointer. You can do that if you want. So if you have an optional of not null of a pointer, then it's actually very, very clear. I really like the semantics of that, because then you say the pointer is never supposed to be null, but it's optional if it's there or not. And then you take the maybiness kind of away from the pointer and into the optional. So it's like, semantically, it's very nice, but in practice, I don't know. I haven't tried it. It will be a bit more cumbersome. But yeah, you can have an optional not null pointer. I think we have 7 seconds left.
Just if your compiler doesn't implement optional, set optional.
Time is out, sorry. Yeah.
No, but like, is there a nice library implementation you can just pull down to?
Yeah. There's boost optional, which was the inspiration for std optional. So you can use that. But if you can't use boost, maybe your clients don't want to use boost, or if you really would like to use std optional, maybe you could just wait a year or two until you can use C plus 17. I was talking to a guy from Qt yesterday, and they have this problem all the time. They had to make a string before you got the proper std string. They had to like make their own types for everything. And you can't really just replace it because you have all of these clients using the. So if you make your own optional or if you use boost optional, you're kind of stuck with that.
You can also implement the std optional. That is the standardized version of the std optional, which we did for C++ 98. Because it's one of the more simpler.
Yeah, it's really simple. You just in the constructor you just have a bool member and a pointer, and in just the constructor you just reserve the memory for the size of the object that you're going to be optional of, and then you can just copy it in there. Yeah, I think that's it. So thanks for coming.